Hi, I am Shanaz. So in this lecture we'll prove some short results about the coloring of a graph, vertex coloring of a graph. So let us start with this theorem. So this theorem states that every tree with bigger or equal to 2 vertices is two chromatic. So every tree with say n bigger or equal to 2 vertices is 2 chromatic. Now let us recall first what do we mean by a tree. So a tree is actually a connected graph which is not having any cycle. Suppose let us consider this graph here. So this is a tree because this graph is free from cycles and it is given to be, so it is first has no cycles, and the second condition is that it is connected. So if these two conditions are satisfied by a graph, that graph is called a tree. So what we are going to prove here, we are going to prove here that any graph having bigger or equal to 2 vertices is 2 chromatic. That means we just need 2 colors to color the vertices of a tree having bigger or equal to 2 vertices. But before proving this result, let us recall the definition of a path. So suppose we are given a graph so this is the graph G having these vertices v1, say v2, v3, v4, v5 and v6. Now a path between two vertices is actually an alternating sequence of vertices and edges, and this sequence starts with this sequence starts with the vertices. So if we look at the vertex v1 and v5, so we have this. Let us also mark these edges. So this is edge e1, this is edge e2, e3, e4, e5, e6 and e7. So if we have to look for paths between vertices v1 and v5, and this is one path. So we start with vertex v1, then v1 is followed by this edge e1, e1 is followed by v3, v3 is followed by e2, and e2 is followed by v5. So this is a path between vertices v1 and v5. So one can observe here this path starts at vertex v1 and ends at vertex v5. So the vertices involved and the edges involved in this path are distinct. So no two vertices are distinct, neither the so no two vertices are the same, neither the edges are same. So the number of edges appearing in this path is called the length of the path. So here we have 2 edges, so the length of this path is 2. So this is the path of length 2 between v1 and v5. Now there is this question, do we have only one path here in this graph between the vertices v1 and v5? Well, the answer in this case is no, because if we look at this path, so let us mark this with red color. So if we look at this path first, then go like this and here and here. So this is the another path. So we started at vertex v1, then e1, then v3, then e7, then v2, then e6, and then v6, then e5, and finally v5. So this is again a path between vertices v1 and v5, and the length of this path here is 4 because we have these 4 edges v1, e1, e7, e6, and e5. Now the distance between vertices vi and vj, let us consider in this case the distance between vertices v1 and v5. So let us denote this distance by d. So this represents the distance between v1 and v5. This is actually defined to be the length of the smallest possible path between v1 and v5. So if there is no such path, if there is no path which connects v1 and v5, then this distance is defined to be the infinite. So this number is infinite if we have no path between v1 and v5. But here in this case we have I think more than 3 number of paths. So this was the first one, this is the second one. We can also come like this finally here. So these are the 3 paths here, and minimum possible length path is this path, the first one. So the length between v1 and v5 here in this case is 2. Now let us move back to this result. So let us consider say any tree. Suppose let us take this tree here. So this is our tree T. So we have to prove this is 2 chromatic. So let us start the proof. So let us consider T be a tree. So let T be a tree with bigger or equal to 2 vertices. So it has, this tree is having n vertices where n is given to be bigger or equal to. Now let us consider any arbitrary vertex here. Let us choose this vertex here. Let us call this vertex v. So consider any vertex v of t. Consider any vertex v of t. So we are good so far. Now what we do, we assign some color to vertex v here. So let us assign this pink color to vertex v1. So vertex v. So this vertex is done. Now let us call this color, this pink color, color 1. So what we do here, so assign color 1 to v. Now let us look all vertices which are neighbors to vertex v. I mean all vertices which are at a distance 1 from vertex v. Clearly these are the vertices. So this vertex here. So let us call this v1, v2, v3, v4. So these are the vertices which are at a distance of 1 from vertex v, I mean which are adjacent to v. Obviously we have to color these vertices with a different color. So let us choose this color blue here. So let us color these vertices with blue color. So next what we do, next what we did, so then now let us call this blue color color 2, then so then assign color 2 to all vertices, which are at a distance of 1 from v, that is the vertices which are adjacent to v, that is the vertices which are adjacent to v. So we are assigning them color 2, which is the blue color. Similarly, now we are going to look for the neighbors of these vertices. So let us call these vertices which are the neighbors of v, let us call these vertices v1, v2 through vr. So let v1, v2 so on vr be the vertices which have been assigned color 2. Which have been assigned color 2. So here in this case the color 2 is assigned to the vertices v1, v2, v3 and v4. Now what we do next is that let us assign color 1 to all vertices which are adjacent to these vertices v1, v2, v3, v4, I mean the vertices which are at a distance of 2. So now assign color 1 to the vertices adjacent to v1, v2 so on vr. Now here in this case the vertices assigned to these adjacent to these vertices are, so if we look at v1, now v1 is adjacent to these 3 vertices v and these 2 vertices. Let us color these vertices with color 1. Similarly v2 has these 3 neighbors 1, 2 and 3. Let us color these with color 1. This is already colored. Now for v3 it has no other neighbor, it has no neighbor other than v. Similarly v4 has no other neighbor other than this. So actually we have missed this vertex, so this is vertex v5. This must be painted below. So v5 is, we have to color v5, the neighbors of v5 with color 1. So in this case we have just finished the coloring. So now assign color 1 to the vertices adjacent to the to the vertices v1 v2 vr and so on. So we continue this process till every vertex in T has been assigned the color. So sorry, so continue this process till every vertex in T has been assigned the color. So in this process we observe that in T all vertices which are at odd distance from V are colored with vertex 2, and all vertices which are at distance even distance from V are colored with the color 1. So observe, suppose we have another vertex here which is at a distance of suppose 3. So this is distance 1, this is distance 1 2. Suppose we have another vertex and another edge here. So this is the vertex here which is at a distance of 3 from V, which is at odd distance from V. So we can color this vertex with blue, which is our color 3. So the vertices which are at odd distance from V are being colored with blue, i.e. the color 2, and all those vertices which are at distance 2, the even distance, are being colored with color pink, which is the color 1. And this vertex is at a distance of 3 from V, so it has to be colored with blue color, the color 2. So observe that in T all vertices which are at odd distance from V are assigned color 1, color 2, sorry, are assigned color 2, and the vertices which are at even distance from V have color 1. Therefore, along any path along any path in T, the vertices are of alternating colors. One can see over here. So if we look for a path from this vertex to this vertex, so this is a path. So we have this alternating coloring. First we have pink, then blue, pink, blue, and so on. So therefore along any path in T, the vertices are of alternating colors. Now in a tree we cannot have two paths between two vertices. So if we look at this graph, we cannot have, we have more than one path from vertex v1 to v5, but this is not the case in tree. For example, if this is the vertex v1 and this is the vertex v5 suppose, and this is the vertex suppose v2, so we have one and only one path between any two vertices in a tree. So this is the path between v1 and v5. So there cannot be one more path. So if there is some other path, suppose if we have this path v1, which is a path of length 1 from v1 to v5, then we will end up with this cycle. But we know the fact that a tree is a graph which is free from cycles. So in a tree between any two distinct vertices, we have exactly one path. We cannot have more than one path, otherwise we end up with cycles. So one can note here, therefore along since there is one and only one path between any two vertices in a tree, no two adjacent vertices have the same color. Since there is exactly one path between any two vertices, of T, no two adjacent vertices have the same color. No two adjacent vertices have the same color. The reason being the vertices at odd distance have color 2 and with even distance have color 1. Hence chi of t is 2. So this proves this result. Now let us do one more result here. This is called the Konig's theorem. So this is the theorem given by Konig, named after Konig. So it states that a graph is two chromatic if and only if it has no odd cycles. So the status that a graph is two chromatic, i.e. bicolorable, if and only if it has no odd cycles. Now to prove this result, we are going to use the previous result. So to prove this result, we'll first recall what do we mean by a spanning tree. Suppose we have this graph here. So this is the labeling v1, v2, v3, v4, v5, v6. So this is the graph on 6 vertices. Now obviously this is not a tree because it contains cycles, so it has to be free from cycles in order to be a tree. Now what do we mean by a spanning tree? So if this is the graph G, then we call a subgraph T of G to be the spanning tree of G if T is a tree and consists of all vertices of this graph G. Now let us look for a subgraph of G which is a tree such that the tree consists of all vertices of G. Now if we look at this subgraph here, so let us look at this subgraph. So it consists of v1, v3, then v4, then v5, v6, and finally this edge. So obviously these edges in red color, this subgraph in red color is a tree, and this is a tree which consists of all 6 vertices. So this T is the spanning tree of G. Now a tree may have more than one spanning a graph G has more than one spanning tree. Now if this T is a spanning tree of G, these red edges are called the branches of G with respect to the spanning tree T, and these black edges v2, v3 and v4, v6, they are called the chords of graph G with respect to the tree T, the spanning tree T. Now these branches and these chords, they may change if we change the spanning tree. Now let us look at this spanning tree. So if we look at this spanning tree, so in previous case these two edges were the chords and the remaining edges were branches in the previous case. Now if we look at this spanning tree here, now this is the spanning tree, this subgraph is the spanning tree. Now in previous case v2, v3 was a chord, but here in this case it is a branch. Now the branches and the chords may alter if we change the spanning tree. So in previous case, if T1 with red color, here this T1, so if we look at the spanning tree T1 which was shown in the previous case, v2, v3 was a chord, but in this case, if we choose this blue subgraph with a spanning tree, v2, v3 happens to be a branch. So a graph G may have more than one spanning tree, and corresponding to a spanning tree of a graph G, we define the branches and the chords. So a branch of a graph G with respect to the spanning tree T are simply the edges in T, and the remaining edges of G are called the chords with respect to that spanning tree. So we'll prove this Konig's theorem in the next lecture.